Long before routers hummed in quiet server rooms, and long before homes glowed with Wi-Fi signals floating silently through the air, communication was slow, linear, and tied to the physical world. Messages traveled as paper, wires clicked with the rhythm of early telegraphs, and computers existed as isolated islands. But somewhere between those separate machines and the connected world you know today, a quiet revolution took shape, one that would turn scattered devices into a global breathing network of information. Chapter 1: Origins of Networks. Before computer networks existed, computers behaved like sealed, self-contained universes. Each machine stored its own data, processed its own instructions, and ended its work within its own metal frame. Nothing moved between systems unless someone physically carried it: magnetic tape, punched cards, or printed output. Networking began with a simple question: what if computers could talk to one another? That question guided decades of engineering, theory, and experimentation, gradually shaping the foundation for the connected digital world. The earliest steps came through time-sharing systems in the late 1950s and early 1960s. These large mainframes were designed to serve many users at once, each connected through terminals. This wasn't yet networking, but it introduced the idea of shared computer resources and the value of multiple endpoints interacting with a central processing system. Terminals could not communicate with each other, but they introduced the architecture of many-to-one, a structure that networks would eventually expand into many-to-many. The late 1960s brought one of the most significant developments in the history of networking: packet switching. At the time, voice networks like the public telephone system relied on circuit switching, which required establishing a dedicated communication path between callers. This was fine for telephone conversations, but inefficient for bursty, unpredictable computer data. Engineers needed a method that allowed information to flow flexibly, even if parts of the communication path were disrupted. Packet switching provided that solution. Instead of reserving a continuous line, data would be broken into smaller units, packets, each carrying source, destination, and content information. These packets could travel independently across a network, taking any available route, and reassemble at the destination. This method transformed the reliability and efficiency of digital communication. If one route failed, packets simply moved through another. The concept became central to ARPANET, the first major packet-switched network, funded by the United States Department of Defense's Advanced Research Projects Agency in 1969. ARPANET connected research institutions like UCLA, Stanford, and UCSB, forming the first working model of a decentralized, resilient communication system. For the first time, computers could send information to one another across great distances without physical transfer. The early ARPANET nodes exchanged messages, files, and remote logins, establishing the foundation for almost every modern network protocol. By the early 1970s, engineers recognized the need for a universal language, a way for networks of different designs to talk to each other. This led to the creation of the Transmission Control Protocol, TCP, and later the separation into TCP and Internet Protocol, IP. Together, these became TCP/IP, the backbone of modern internetworking. IP handled addressing and routing, determining where data should go, while TCP ensured reliability, ordering, and error correction. This separation of responsibilities created a flexible architecture that allowed new networks to join the system without redesigning every component. As TCP/IP matured, ARPANET expanded and more institutions connected. Email became one of the earliest and most transformative applications, proving how digital communication could replace traditional methods with extraordinary speed. Throughout the 1980s, universities, laboratories, and eventually entire countries joined the growing web of interconnected machines. This was no longer a small research system. It was a genuine global network. In 1983, TCP/IP became the standard protocol for ARPANET, marking what many consider the birth of the modern Internet. This decision unified network design principles and created a consistent model for building and connecting systems worldwide. Over time, ARPANET itself faded, eventually retiring in 1990, but the architecture it established remained, expanding through private networks, academic institutions, and eventually commercial service providers. The rise of local area networks, LANs, in the 1980s added another dimension to the networking landscape. Instead of focusing only on long-distance communication, organizations wanted computers in the same room or building to communicate efficiently. Technologies like Ethernet emerged as practical solutions for short-range, high-bandwidth networking. Originally competing with other technologies like token ring, Ethernet gradually became the dominant LAN technology thanks to its simplicity, scalability, and cost efficiency. Ethernet began with thick coaxial cables and bus topologies, where every device shared a single communication line. Over time, it transitioned into twisted pair copper cabling, star topologies, and eventually switching technologies that eliminated collisions and improved performance. Modern Ethernet now supports speeds that early designers could never have predicted, ranging from 10 megabits per second in its earliest commercial form to multi-gigabit and even 100 gigabit architectures in enterprise environments. The 1990s saw an important shift. Networking moved from being a specialized tool used in universities and research centers to an everyday consumer technology. Home computers gained network cards, and dial-up internet provided basic connectivity to millions. Browsers emerged, transforming the internet from a system for data exchange into a world of visual exploration. The web became the most influential networking application in history, but beneath the pages and links was the architecture built across decades of careful engineering. Wireless networking followed a similar path. Early experiments paved the way for the IEEE 802.11 standard, allowing devices to communicate without physical cables. What began with slow, short-range connections evolved into high-speed Wi-Fi, eventually becoming a fundamental part of modern life. Phones, laptops, home appliances, and countless smart devices now rely on wireless access points as gateways to larger networks. Today, computer networks span every scale. Personal networks exist within homes. Local networks operate in offices, campuses, and enterprises. Wide area networks connect distant branches of organizations. Global networks form the backbone of communication, commerce, and knowledge exchange. Every device, from small sensors to large data centers, participates in a layered web of communication shaped by decades of foundational research and engineering. This chapter presents the quiet beginnings of a massively interconnected world, from isolated machines and physical media to global packet-switched networks. The evolution of networking forms the basis for everything that follows in the modern computing landscape. As we move into deeper chapters, the story transitions from origins into the fundamental principles that govern how networks operate today, addressing routing, switching, and the layered models that structure the entire digital world. Chapter 2: Foundations of Communication. Modern computer networks rest on a structure of principles that allow devices to exchange information reliably, predictably, and at scale. These principles form the invisible framework that keeps data flowing between endpoints, no matter the distance or complexity of the path. To understand how networks function today, it helps to begin with the foundational models developed to make communication consistent across different devices, platforms, and technologies. These models define how information should be prepared, transmitted, routed, received, and interpreted. Two major conceptual models guide nearly all network design: the OSI model and the TCP/IP model. Although one is theoretical and the other practical, both provide a structured way to think about how communication occurs. They separate complex processes into manageable layers, with each layer responsible for a specific set of functions. This separation helps engineers create technologies that can work together, even if they are designed by different organizations or built for different hardware platforms. The OSI model, introduced in the late 1970s by the International Organization for Standardization, divides communication into 7 layers. At the lowest level sits the physical layer, which describes the transmission of electrical or optical signals through wires, fiber, or wireless media. Above it is the data link layer, responsible for framing, error detection, and local delivery within a network segment. The network layer handles logical addressing and routing, ensuring that packets can reach destinations across multiple interconnected networks. The transport layer sits above the network layer and manages end-to-end communication, reliability, and flow control. It ensures that data arrives in the correct order and without corruption. The session layer establishes and manages connections between systems. The presentation layer formats data, handling encryption, compression, and representation. At the top, the application layer provides the interfaces used by software to communicate across networks. Each layer depends on the service provided by the layer below it and supports the layer above it, creating a clean, modular structure. While the OSI model is widely taught, real-world networking primarily uses the TCP/IP model, a simpler and more practical 4-layer system aligned with Internet standards. Its layers, link, Internet, transport, and application, combine functions from the OSI structure but maintain the same conceptual purpose, organizing communication in a clear layered hierarchy. The link layer handles local network protocols like Ethernet and Wi-Fi. The Internet layer contains IP, responsible for addressing and routing. The transport layer includes TCP and UDP, managing reliability and data flow. The application layer includes protocols like HTTP, DNS, and SMTP. Layering works because it creates abstraction. Engineers can improve or redesign one part of a network without disrupting the rest. For example, Wi-Fi standards can evolve from early 802.11b to modern 802.11x without changing how routers interpret IP addresses or how web browsers request content. Similarly, improvements to TCP congestion control algorithms do not require changing physical cabling or application interfaces. Each layer hides its internal complexities and exposes only a predictable interface to the layers above and below. Addressing forms another core foundation of communication. Every device on a network must have a unique address to send and receive data. The primary system used today is IP addressing with 2 major versions, IPv4 and IPv6. IPv4 uses 32-bit addresses written in dotted decimal notation such as 192.168.1.10. It supports roughly 4 billion addresses, which was sufficient for early networks, but became limiting as billions of devices came online. To extend the lifespan of IPv4, engineers developed methods like network address translation, which allows many internal devices to share a single public address. IPv6 uses 128-bit addresses written in hexadecimal notation, providing an extremely large address space. This system was designed to support the growing volume of devices, cloud systems, mobile phones, sensors, and embedded technologies. Although IPv6 adoption has grown steadily, many networks still operate in a hybrid environment supporting both IPv4 and IPv6. Routing protocols, operating systems, and hardware, increasingly support dual-stack operation, offering compatibility with both address families. Beyond addressing, networks depend on the concept of routing, which determines how packets travel from a source to a destination across multiple networks. Routers examine packet headers and make forwarding decisions based on routing tables. These tables can be built manually or automatically through routing protocols. Static routing works for simple networks, but dynamic routing protocols handle complex and changing environments. Examples include RIP, OSPF, ISIS, and BGP, each designed for different scales and topologies. Local communication relies on switching, which operates within network segments. Switches use MAC addresses to forward frames only to the appropriate port, reducing unnecessary traffic and improving efficiency compared to older hub-based networks. Modern switches support full duplex communication, VLAN segmentation, quality of service policies, and link aggregation, creating highly flexible and scalable LAN architectures. Another foundation of network communication is the concept of encapsulation. When data is prepared for transmission, it moves down the layers of the model, gaining additional headers at each stage. An application message becomes a transport segment, then a network packet, then a link layer frame. Each layer wraps the data with its own metadata, enabling proper delivery and processing. At the receiving end, the process reverses as each layer removes its header, eventually delivering the original message to the correct application. Encapsulation supports modularity and ensures each layer only needs to interpret the information relevant to its function. This is why packets can travel across networks that use different physical media, routing protocols, or link technologies. The structure of encapsulated data remains consistent throughout the journey, even as the underlying transport changes. Error detection and correction also play essential roles. Frames and packets include checksums or cyclic redundancy checks to detect corruption. Some systems request retransmission, while others simply discard flawed data. TCP implements reliability through acknowledgements and retransmission mechanisms, while UDP allows faster but less reliable communication. The balance between reliability and speed helps networks support a wide range of applications, from streaming and voice communication to financial transactions and remote access. Finally, the growth of networks led to the development of naming systems. Humans are not well suited to memorizing long numerical addresses, so the domain name system was created to map meaningful names to IP addresses. DNS distributes responsibility across hierarchical servers, allowing domains to be managed independently while remaining part of a global namespace. This system ensures that entering a familiar address leads to the correct resource, even as infrastructure changes. These foundational principles, layering, addressing, routing, switching, encapsulation, error control, and naming, support every modern network. They create a predictable, structured environment in which countless devices communicate daily. Without them, the complexity of global communication would be unmanageable. They form the core knowledge required to navigate deeper topics, including protocols, topologies, security, and performance optimization. Chapter 3: Core Network Components. Every computer network, regardless of size, depends on physical and logical components that enable communication. These components transform abstract principles into operational systems, capable of moving data reliably between devices. Understanding these components helps reveal how networks function beneath their quiet background presence. Though often unseen, they form the architecture that supports everything from home Wi-Fi to global communication infrastructures. At the physical level, networks rely on transmission media that carry electrical or optical signals. Copper cabling has remained a fundamental technology for decades, evolving through categories that offer improved bandwidth and reduced interference. Twisted pair cables such as Cat5e, Cat6, and Cat6a use pairs of tightly wound copper wires to minimize crosstalk. They support speeds ranging from 100 megabits per second to multiple gigabits depending on length and standard. Coaxial cables, once common in early Ethernet networks, still serve roles in broadband internet connections through cable modem systems. Fiber optic cables represent the highest performance medium, transmitting light signals through glass or plastic fibers. They offer long-distance, high-bandwidth communication, low signal loss, and immunity to electromagnetic interference. Beyond cabling, wireless technologies extend networks through radio waves. Wi-Fi became one of the most transformative networking technologies, allowing devices to connect without physical wiring. Wireless standards have progressed from the early 802.11b standard, with speeds of 11 megabits per second, to modern 802.18x technologies offering multi-gigabit performance. Wi-Fi access points coordinate communication among wireless devices and link them to the wired network infrastructure. Their placement, channel configuration, and power levels influence coverage, performance, and reliability. At the heart of local networks are network interface controllers, NICs. These components, integrated into motherboards or installed as separate cards, convert digital data into electrical or optical signals for transmission and handle low-level communication tasks. NICs contain MAC addresses, unique identifiers assigned to each device, enabling switches to direct frames accurately. As technology improved, NX incorporated advanced features, including offloading tasks like checksumming and segmentation to reduce CPU load. Switches are central to Ethernet-based LANs. They forward frames intelligently using MAC address tables, reducing unnecessary broadcasts and improving efficiency. Early switches relied on store and forward operation, receiving entire frames before forwarding them. Cut-through switches improved performance by forwarding frames as soon as destination addresses were read, though at the risk of forwarding corrupted data. Modern switches often combine these approaches while adding features like VLANs, link aggregation, spanning tree protocols, and port security. Managed switches provide fine-grained control over network behavior, while unmanaged switches offer simple plug-and-play functionality. Routers operate at a different level, managing communication between networks. They examine IP headers, apply routing logic, and forward packets toward their destinations across diverse paths. Routers maintain routing tables that can be configured manually or populated through dynamic routing protocols. They also implement network address translation, enabling internal networks to share public IP addresses. Enterprise routers may incorporate firewall capabilities, VPN services, and traffic management tools. Service provider routers operate at national or global scale, carrying huge volumes of data through complex, resilient infrastructures. Firewalls are another critical component, controlling traffic based on security policies. Traditional firewalls filtered traffic based on IP addresses, ports, and protocols. Next-generation firewalls analyze application signatures, encrypted traffic, and user identity, offering deeper inspection. Firewalls can operate at network boundaries between internal segments or on individual hosts. They protect networks from unauthorized access while providing visibility into traffic patterns and threats. Wireless controllers serve similar roles for Wi-Fi environments, especially in large organizations. They centralize the management of access points, coordinating channel assignments, power levels, roaming behavior, and security settings. By treating wireless access points as a unified system rather than isolated devices, Controllers enhance stability and performance across campus-wide networks. In addition to these forwarding devices, modern networks depend on servers that provide essential services. DHCP servers assign IP addresses automatically, reducing manual configuration and supporting dynamic devices. DNS servers translate domain names into numerical addresses. Authentication servers validate user credentials, allowing secure access to resources. File and application servers distribute data, software, and shared content. In cloud environments, these services may be distributed across data centers, but their role remains the same, supporting the functions that keep networks organized and accessible. On the logical side, networks rely on protocols, the standardized rules that govern communication. Protocols exist at every layer of the networking model. At the link layer, Ethernet defines frame structure and media access rules. At the network layer, IP defines addressing and routing. At the transport layer, TCP and UDP define data delivery mechanisms. At the application layer, a wide array of protocols support specific purposes: HTTP for web communication, SMTP for email, SSH for secure remote access, and countless others. Protocols ensure that devices, regardless of manufacturer or operating system, can exchange information reliably. Addressing and naming systems form another essential logical component. IP addressing allows devices to communicate across networks, while DNS resolves human-friendly names to numerical addresses. MAC addressing supports local communication. Subnetting divides networks into logical segments, improving organization, security, and performance. These systems work together to support scalable, flexible communication. Network topology influences how components connect and interact. Common topologies include star, mesh, bus, and hybrid arrangements. Star topology, used in most modern LANs, connects devices to a central switch. Mesh topology offers redundancy by connecting every node to multiple others, commonly used in wireless systems or backbone networks. Bus topology once dominated early Ethernet, but has largely disappeared in favor of more reliable structures. Hybrid topologies combine elements to meet specific performance, reliability, or organizational requirements. As networks scale, redundancy becomes critical. Redundant links, switches, routers, and power supplies provide resilience against failures. Protocols like the spanning tree protocol prevent loops in redundant Ethernet networks. Link aggregation combines multiple physical links into a single logical connection, increasing bandwidth and providing backup paths. High availability configurations ensure that critical systems remain operational even when individual components fail. These measures support the reliability expected of modern networks, which now serve as essential infrastructure for communication, commerce, and daily life. Environmental considerations also shape network design. Cabling standards define maximum lengths, bend radiuses, and installation practices to maintain performance. Data centers require controlled cooling, power distribution, and secure physical layouts. Electromagnetic interference must be minimized, especially in environments with heavy machinery or radio equipment. Careful planning ensures that networks operate efficiently and reliably under a wide range of conditions. Monitoring systems let administrators observe network performance, detect anomalies, and address issues before they become disruptive. Tools like SNMP, NetFlow, and logging services provide data about traffic, errors, utilization, and device status. Automation systems can adjust configurations, reroute traffic, or issue alerts through predefined rules. Monitoring ensures that networks remain transparent and manageable, supporting both everyday operations and long-term planning. Together, these components, physical media, forwarding devices, servers, protocols, topologies, redundancy systems, and monitoring tools, form the architecture of modern networks. Each plays a role in ensuring that data moves predictably and securely. As we continue into deeper chapters, we shift from the components themselves to the behaviors they support. How networks route traffic, control congestion, avoid collisions, and maintain stability across diverse environments. Chapter 4: Routing, Switching, and Traffic Flow. Modern networks depend on efficient movement of data, whether a small packet travels across a local office or crosses international fiber links. Every step of the journey relies on routing, switching, and traffic control. These systems ensure that communication remains orderly, predictable, and resilient, even when thousands or millions of devices share the same infrastructure. Understanding how data flows reveals the quiet choreography that makes networks reliable. Switching forms the foundation of local communication. Within a local area network, switches determine where to forward frames using MAC address tables. When a switch receives a frame, it examines the source MAC address and records which port the device is connected to. Over time, the switch builds a complete map of the network's physical arrangement. If a frame arrives with a destination MAC address that the switch recognizes, it forwards the frame to the correct port. If the switch does not recognize the address, it broadcasts the frame to every port except the one it arrived on. Early LAN technology relied on hubs, which repeated every signal to every device on the network. This caused collisions, as multiple devices attempted to send data simultaneously. Switches solved this by providing separate collision domains for each port, enabling full duplex communication and improving performance dramatically. As networks grew, switches added more sophisticated features, virtual LANs to segment networks logically, spanning tree protocols to prevent loops, and quality of service policies to prioritize important traffic. Routing extends communication beyond local segments. Routers operate at the network layer, forwarding packets between networks and making decisions based on IP addresses. Routing tables map destinations to next hop addresses. A packet may pass through many routers, each reading the destination address and sending it toward the appropriate direction. Routing allows networks of different sizes, technologies, and physical locations to interconnect. There are two main types of routing: static and dynamic. Static routes are configured manually and remain unchanged unless an administrator modifies them. They are simple, predictable, and appropriate for small networks. Dynamic routing uses protocols that exchange information between routers automatically. These protocols allow routers to adjust to changes in the network, such as failed links or new segments coming online. Interior gateway protocols handle routing within a single organization. RIP uses hop count as its metric and is suitable for small networks. OSPF uses link cost and supports hierarchical design, allowing for efficient routing across large environments. ISIS operates similarly and is commonly used in service provider networks. Exterior gateway protocols handle routing between organizations. BGP controls global internet routing, exchanging path information among thousands of autonomous systems. Congestion and traffic management form another essential component of network behavior. As data flows through shared links, routers must decide how to handle bursts of traffic. Congestion control mechanisms ensure that networks do not become overwhelmed. TCP implements its own congestion strategies through window sizes, acknowledgements, and rate adjustments. Routers can implement queuing strategies, such as FIFO, weighted fair queuing, or priority queuing, to shape traffic based on importance or bandwidth requirements. Switching and routing work together to support efficient data flow. A device sends data into the local network, A switch forwards it to a router, and the router guides it toward its destination through the most efficient path available. Each step is independent yet coordinated. If one path fails, routing protocols find alternatives. If traffic spikes, congestion mechanisms work to preserve stability. This layered approach ensures continuity even during unexpected events. Multicast and broadcast handling further refine traffic flow. Broadcast messages reach all devices within a segment, useful for discovery protocols, but limited in scope to avoid unnecessary traffic. Multicast communication targets groups of devices supported through protocols like IGMP and PIM. These methods optimize communication for applications like streaming, conferencing, and distributed systems that need to deliver the same data to multiple endpoints. As networks scale, architecture matters. Hierarchical models, commonly divided into core, distribution, and access layers, organize devices for efficiency and reliability. The access layer connects end devices. The distribution layer aggregates access switches and enforces policies. The core layer focuses on fast, resilient transport between major parts of the network. This structure minimizes bottlenecks and simplifies troubleshooting. Routing, switching, and traffic control allow networks to behave predictably despite constant change. Devices come online, links fail, applications vary in bandwidth demands, and users move between wireless access points. Yet through structured design and adaptive protocols, networks maintain smooth, continuous communication. This chapter establishes the movement of data as a foundational concept that supports all higher-level services and applications. In the chapters ahead, we explore how real-world networks are designed and implemented using these principles. Chapter 5: Network Design, Topologies, and Architecture. Designing a network requires balancing performance, reliability, scalability, and simplicity. These goals shape the architecture of everything from home setups to enterprise environments and global service provider systems. Good design begins with understanding how devices should connect, how traffic should flow, and how failures should be handled. With proper planning, networks remain stable even under unpredictable conditions. Topologies describe physical or logical arrangements of devices. In a star topology common in modern LANs, each device connects to a central switch. This isolates failures and simplifies troubleshooting. In a mesh topology, devices connect to multiple others, creating resilient paths. Full mesh provides maximum redundancy but is impractical at scale. Partial mesh offers a balance between resilience and cost. Bus topologies, once used in early Ethernet networks, have largely disappeared due to collision issues. Ring topologies offer predictability and were used in token ring networks, though they have also fallen out of use. Network design often uses hierarchical architecture. The access layer connects end devices, computers, phones, printers, cameras. The distribution layer aggregates access switches and enforces boundaries, including routing decisions, VLAN segmentation, and policy control. The core layer connects major segments at high speed, ensuring low latency communication across the network. This three-tier model provides a structured approach to building scalable, manageable environments. For smaller networks, a two-tier model, collapsed core, combines core and distribution layers. This reduces complexity while preserving essential functionality. Large organizations may adopt spine and leaf architectures common in data centers. In this model, leaf switches connect directly to servers and access devices, while spine switches provide a high-speed backbone. Every leaf connects to every spine, ensuring predictable performance and reducing bottlenecks. Segmentation improves both performance and security. VLANs divide networks into logical groups, regardless of physical location. This reduces broadcast domains and organizes devices by department, function, or security level. Inter-VLAN routing enables communication between segments while maintaining control over access policies. Segmentation also limits damage if part of the network experiences issues or attacks. Redundancy is essential for reliability. Links, switches, routers, and power systems can all fail, so network architects include backup paths and devices. Spanning tree protocol prevents loops in Ethernet networks, while link aggregation combines multiple physical connections into a single logical interface. Router redundancy protocols, such as VRRP, HSRP, or GLBP, ensure continuity even if a default gateway goes offline. Service provider networks use multiple upstream connections to maintain internet access during outages. Wireless design introduces new considerations. Access points must be placed to minimize interference, provide consistent coverage, and support roaming. Channel planning avoids overlapping frequencies. Modern 5 GHz and 6 GHz bands offer greater performance but shorter range, requiring careful density planning. Wireless controllers coordinate AP behavior across large environments, adjusting power levels and channels dynamically. Cabling infrastructure shapes long-term network health. Standards specify maximum distances for copper and fiber runs. Structured cabling systems organize connections through patch panels, racks, conduits, and labeled pathways. Proper installation ensures predictable performance and simplifies maintenance. Data centers require cooling, power distribution, grounding, and environmental monitoring to protect network equipment. Security plays a central role in design. Networks include firewalls at perimeter boundaries, IDS or IPS systems for threat detection, and segmentation to isolate sensitive areas. Design decisions consider least privilege principles, controlling access based on roles and functions. Encryption protects data in transit, especially across public networks. Authentication systems validate users, and authorization policies restrict access to approved resources. Scalability remains a constant requirement. Networks must support growth without major overhauls. Modular switch designs allow additional line cards. Virtualization technologies, virtual switches, virtual routers, and virtual firewalls enable flexible expansion. Cloud connectivity integrates on-premise and remote resources through secure tunnels or dedicated circuits. A well-designed network balances simplicity and capability. The goal is not to use every feature available, but to build a resilient, comprehensible structure that meets organizational needs. In the next chapter, we examine how these designs integrate with modern computing environments, including virtualization, cloud services, and distributed applications. Chapter 6: Modern Network Services and Virtualization. As computing environments evolved, networks expanded beyond simple data, forwarding into platforms for services, virtualization, and distributed applications. Modern networks support dynamic workloads, cloud environments, remote access, and software-defined control. These capabilities transform networks into flexible, programmable systems that adapt to changing demands. Virtualization reshaped how networks operate. Traditionally, servers ran on dedicated hardware, and networks were tightly bound to physical devices. With virtualization, multiple virtual machines can run on a single host, each requiring network connectivity. Virtual switches operate within hypervisors, forwarding traffic between virtual machines and linking them to physical networks. These virtual switches enforce VLANs, filtering, security policies, and traffic shaping just like physical switches. Network virtualization extends this concept further. Virtual routers, firewalls, and load balancers replicate the functions of physical appliances, offering flexibility without requiring hardware installation. Software-defined networking, SDN, separates the control plane from the data plane. Instead of each device making its own forwarding decisions, a centralized controller programs network behavior. This enables automation, consistent policy enforcement, and rapid reconfiguration. Cloud computing relies heavily on virtualized networking. Public cloud providers create virtual private clouds that mimic traditional network structures, but exist entirely in software. Administrators define subnets, routing rules, security groups, and gateways through control panels or APIs. Traffic moves through virtual routers, and services scale automatically to meet demand. Hybrid cloud architectures connect on-premise networks to cloud environments through VPN tunnels or dedicated links. Load balancing is another critical service. As applications distribute workloads across multiple servers, load balancers ensure even traffic distribution and reduce downtime. They operate at various layers, from simple round-robin distribution to advanced application layer inspection. In cloud environments, load balancing becomes elastic, scaling based on traffic patterns. DNS, DHCP, and authentication remain fundamental services. DNS maps domain names to IP addresses, enabling user-friendly navigation. DHCP automates IP address assignment, simplifying device management. Authentication services verify identity, supporting secure access to resources. These services may run on-premise, in cloud environments, or in hybrid configurations. Remote access technologies evolved significantly. Virtual private networks encrypt communication between remote users and central networks, allowing secure work from anywhere. SSL VPNs operate through browsers, while IPsec VPNs integrate directly with operating systems. Zero-trust models extend remote access by validating identity continuously rather than relying solely on network boundaries. Monitoring and observability form critical components of modern services. Tools collect metrics on bandwidth usage, latency, packet loss, and device health. Logs provide historical insight into events. Flow data reveals communication patterns between systems. Network management platforms use this information to automate responses, create alerts, and guide capacity planning. Cloud-native networking introduces new layers of complexity. Container orchestration platforms like Kubernetes manage internal networking between containers, providing virtual networks, service discovery, and load balancing. Microservices architectures generate large volumes of east-west traffic, requiring efficient internal routing and observability. Service meshes add encryption, traffic control, and resilience within application layers. Together, these modern services and virtualization technologies transform networks into flexible, scalable systems. They support distributed applications, remote workforces, cloud computing, and high-performance environments. In the next section, we move towards security, exploring how networks defend themselves within an increasingly connected world. Chapter 7: Network Security Fundamentals. Network security forms the protective layer that shields modern communication systems from disruptions, misuse, and unauthorized access. As networks expand, connect more devices, and support increasingly complex applications, the risk of exploitation grows as well. Security is no longer something added after design. It is a core requirement woven into every layer of communication. Understanding its fundamentals provides a stable foundation for all future concepts in network protection. At the heart of network security lies the CIA triad, a simple but powerful model representing confidentiality, integrity, and availability. These principles guide the design of policies, technologies, and defenses. Confidentiality ensures that information remains private. Integrity ensures that data is accurate and unaltered. Availability ensures that services remain accessible when needed. Every security technology ultimately supports one or more of these goals, whether through encryption, verification, redundancy, or access control. Confidentiality relies heavily on encryption, which transforms readable data into unintelligible form unless decrypted with the correct key. Encryption protects information as it travels between devices and across different networks. Protocols like TLS secure web browsing by encrypting data exchanged between browsers and servers. IPsec can create secure tunnels between remote networks or devices. Wireless security standards such as WPA3 encrypt radio traffic to protect communication across open airwaves. Without encryption, any attacker positioned between sender and receiver could intercept or modify sensitive data with little difficulty. Integrity ensures that transmitted data arrives unchanged. Many protocols incorporate checksums or message authentication codes that detect alterations. Hashing algorithms produce fixed-length outputs from variable-length inputs, making tampering easily detectable. Digital signatures combine hashing with encryption to verify both integrity and authenticity. When a device receives a message, it can compare the provided signature or hash with what it generates locally. If the values differ, the data has been modified or corrupted and is rejected. Availability represents the ability of networks and services to function consistently. Attackers often attempt to disrupt availability through denial of service attacks, overwhelming systems with illegitimate traffic. Organizations defend against these attacks through rate limiting, traffic filtering, load balancing, and distributed infrastructure. Redundancy also plays an important role. If one device or link fails, another can continue to support the service. High availability designs ensure that critical resources remain operational, even under stress or failure conditions. Firewalls form a central pillar of network security. Traditional firewalls inspect packets based on IP addresses, ports, and protocols, allowing or denying traffic according to rules. They enforce boundaries between trusted and untrusted networks. Modern environments often rely on next-generation firewalls, which analyze applications, inspect encrypted sessions, and evaluate user identity. These devices recognize patterns associated with attacks, unauthorized behavior, or malware. Firewalls can be deployed at network edges, between internal segments, or on individual hosts, creating layered defenses that limit attacker movement. Intrusion detection and prevention systems complement firewalls. Detection systems analyze traffic and raise alerts when suspicious patterns appear. Prevention systems act automatically, blocking or isolating malicious traffic. Detection can be signature-based, identifying known attacks, or anomaly-based, identifying deviations from normal behavior. These systems strengthen visibility, offering insight into emerging threats or hidden vulnerabilities. Authentication and authorization form another essential security layer. Authentication verifies identity through passwords, biometrics, tokens, or certificates. Authorization determines what authenticated users may access. Together, they ensure that only legitimate individuals or devices interact with network resources. Enterprise networks often use centralized authentication systems, such as Radius or LDAP, to enforce consistent policies across all devices. Multi-factor authentication significantly strengthens identity verification by requiring multiple forms of evidence. Network segmentation enhances security by creating boundaries between different parts of a network. Segmentation reduces the impact of breaches by isolating sensitive systems. VLANs divide networks logically, grouping devices by role or department rather than physical location. Firewalls or access control lists regulate communication between segments. This prevents a compromise in one area from spreading freely across all systems. Segmentation supports least privileged design by ensuring that devices access only the resources necessary for their functions. Monitoring and logging provide visibility into network behavior. Logs capture connection attempts, system events, authentication records, and anomalies. Security information and event management systems collect these logs, analyze patterns, and alert administrators to unusual activity. Monitoring supports both real-time detection and long-term investigation. Without visibility, even well-designed networks can harbor unnoticed vulnerabilities. Patch management also influences network security. Software flaws are continually discovered in operating systems, devices, and applications. Attackers often exploit these weaknesses to gain unauthorized access. Regular updates reduce risk by addressing known vulnerabilities. Automated patching systems help organizations maintain consistency, while scheduled maintenance windows allow updates without disrupting service availability. Network. Infrastructure devices, routers, switches, firewalls, and wireless access points also require firmware updates to repair vulnerabilities. Human factors shape security as well. Many breaches result not from technical exploits, but from social engineering. Attackers use deceptive emails, fraudulent websites, or persuasive messages to trick individuals into revealing credentials or installing malware. Awareness training helps users recognize these attempts. Clear policies, combined with user education, reduce the likelihood of unintentional compromise. Modern security strategies increasingly incorporate zero-trust principles, which assume that no device, user, or connection is inherently trustworthy. Instead of granting broad access based on network location, zero trust requires continuous verification. Access decisions consider identity, device health, context, and policy. Microsegmentation divides networks into very small zones, limiting lateral movement. Encryption protects internal traffic. Authentication occurs frequently, not just at login. This approach reduces exposure and transforms security from a perimeter-focused model into a holistic, identity-driven system. Together, these fundamentals form the base of network security. Encryption protects information. Integrity checks detect tampering. Firewalls and intrusion systems filter traffic. Authentication verifies identity. Segmentation limits movement. Logging provides visibility. Patching reduces vulnerabilities. Human awareness prevents social engineering attacks. Zero-trust principles unify these defenses into continuous adaptive protection. As networks grow more complex, these fundamentals remain central to safeguarding communication and supporting the reliability expected in modern infrastructure. Chapter 8: Wireless Networking and Mobility. Wireless networking has become a central part of modern communication systems, enabling mobility, flexibility, and convenience across homes, workplaces, campuses, and public environments. Instead of relying on physical cabling, wireless networks use radio waves to transmit data between devices. This shift has expanded the reach of network connectivity and created opportunities for entirely new categories of applications. Understanding how wireless networking works begins with its physical characteristics, then extends to standards, performance factors, security, and mobility. Wireless communication operates through electromagnetic signals transmitted over specific frequency bands. The most common technologies used in local wireless networks fall under the IEEE 802.11 family of standards, commonly referred to as Wi-Fi. Early implementations, such as 802.11b, provided modest throughput using the 2.4 GHz band. Over time, newer standards improved reliability, capacity, spectral efficiency, and resilience. The introduction of 802.11a brought the 5 GHz band offering cleaner channels and reduced interference. Later, 802.11g combined features from earlier designs. The adoption of 802.11 marked a major step forward by introducing multiple input, multiple output antenna technology, which increased speed and improved performance in environments with reflections and obstacles. More recent standards, including 802.11ac and 802.11x, enhance modulation schemes, channel widths, and overall efficiency. Access points form the core of wireless networks. These devices broadcast signals that allow clients to establish connections. Access points manage communication through mechanisms that govern how devices transmit data, avoid collisions, and share the medium. They handle authentication, manage encryption, assign association identifiers, and coordinate communication sequences. In larger environments, wireless controllers coordinate groups of access points, enabling consistent configuration, seamless roaming, and centralized monitoring. Radio frequency behavior shapes how wireless networks perform. Signals weaken as distance increases, and materials such as concrete, brick, and metal can significantly reduce signal strength. Multipath reflections occur when signals bounce off surfaces and arrive at the receiver at slightly different times. While early systems struggled with this issue, modern Wi-Fi standards use advanced signal processing to turn multipath behavior into an advantage, combining reflected paths to improve throughput. Interference from household electronics, other wireless networks, and environmental factors affects performance as well. The 2.4 GHz band offers wide coverage but suffers from limited channel availability and significant interference from devices such as microwaves, Bluetooth peripherals, and baby monitors. The 5 GHz band provides more channels, higher throughput, and cleaner signals, though with shorter range. The introduction of the 6 GHz band through Wi-Fi 6E expands the available spectrum dramatically, reducing congestion in dense environments. Each band requires careful planning to achieve optimal results, particularly in multi-access point deployments. Mobility introduces additional behavior. As devices move, they must transition between access points. The roaming process involves identifying neighboring access points, evaluating signal strength, and selecting new connection targets. Uncoordinated roaming may produce temporary disruptions, but enterprise systems streamline the process through controller-assisted decisions, optimized scanning intervals, and fast transition protocols. These mechanisms minimize delays and support uninterrupted connectivity for applications such as voice communication and real-time collaboration. Security is essential in wireless environments. Early wireless security relied on the wired equivalent privacy protocol, which suffered from significant vulnerabilities. Attackers could capture traffic, derive encryption keys, and impersonate devices. WPA replaced WEP with stronger security mechanisms, and WPA2 introduced AES-based encryption for robust protection. WPA3 further improves security by enhancing key exchange methods, providing individualized encryption in public networks, and resisting offline dictionary attacks. Wireless networks also support enterprise authentication through 802.1x, which uses Radius servers to validate users and assign roles before granting access. Different wireless networks require different levels of protection. Personal networks typically rely on shared passphrases. Enterprise environments enforce certificate-based authentication or integrate with existing identity systems. Guest networks often isolate traffic, apply bandwidth restrictions, and require captive portal acceptance. These design elements prevent guest users from accessing internal resources while still providing convenient connectivity. Channel planning is critical in environments with multiple access points. Overlapping channels cause interference, reducing throughput and increasing latency. In the 2.4 GHz band, only 3 channels do not overlap, requiring careful placement and spacing of access points. The 5 GHz and 6 GHz bands provide far more channels, enabling better distribution. Signal power must also be managed carefully. Increasing power does not always improve performance. It may create coverage overlap, cause client devices to latch onto distant access points, or introduce unnecessary interference. Quality of service mechanisms enhance performance for applications sensitive to delay. Wireless networks classify traffic into categories and adjust transmission priorities to support voice, video, and other real-time applications. These features reduce jitter, minimize dropped packets, and create predictable performance under varying levels of congestion. Mesh networking extends wireless coverage by enabling access points to communicate wirelessly with one another. This design reduces or eliminates the need for physical cabling in remote or hard-to-reach areas. Mesh networks perform best when nodes maintain strong connections, and the network design limits repeated wireless hops. While mesh networks offer convenience, wired backhaul remains preferable when high throughput and low latency are required. Wireless networking also supports the growing ecosystem of Internet of Things devices. Many IoT devices rely on specialized protocols designed for low power consumption and small data transfers. Bluetooth enables short-range, low-energy communication. Zigbee supports mesh networking for sensors and home automation. LoRaWAN provides long-range, low-bandwidth communication suitable for wide-area sensor networks. These technologies complement Wi-Fi rather than replace it, each serving distinct use cases. Together, wireless technologies create a flexible and dynamic communication environment. They support mobile devices, real-time applications, sensors, automation systems, and growing cloud workloads. As wireless standards evolve, they continue to expand capacity, improve efficiency, and address new challenges in security and mobility. The next chapter explores how global networks coordinate communication across vast distances, connecting service providers, data centers, and millions of users worldwide. Chapter 9: Service Providers and the Global Internet. The global internet is a vast collection of interconnected networks operated by thousands of organizations, each with its own infrastructure, policies, and responsibilities. No single entity owns the internet. Instead, it functions through cooperation, agreements, engineering standards, and careful coordination. Service providers form the backbone of this system, delivering connectivity across neighborhoods, cities, countries, and continents. Understanding how these providers operate reveals how global communication remains reliable, despite enormous scale and constant change. Service providers are often described in tiers. Tier 1 providers occupy the highest level. They operate large international backbone networks and connect directly to other Tier 1 providers through settlement-free agreements. These networks span continents, ocean floors, and major metropolitan regions. Tier 2 providers purchase transit from Tier 1 networks but may run substantial regional infrastructures. They often peer with other networks to reduce costs and improve performance. Tier 3 providers focus on local access, delivering connectivity to homes, small businesses, and rural communities. Together, these tiers form a hierarchy of reach and capability. All Internet-connected organizations operate their networks as autonomous systems. An autonomous system represents a network or group of networks controlled by a single administrative authority. Each autonomous system has a unique number assigned by regional Internet registries. Autonomous systems exchange routing information using the Border Gateway Protocol. BGP allows networks to announce which IP address ranges they manage and determines how traffic should flow from one autonomous system to another. Routing decisions consider path length, policies, business relationships, and engineering objectives. Through BGP, the Internet remains a connected fabric rather than isolated islands. Physical infrastructure is fundamental to the Internet's operation. Submarine cables carry data between continents, forming the core of international connectivity. These cables consist of fiber optic strands laid along ocean floors and protected by durable outer layers. Repeaters spaced along the cable amplify optical signals, preserving quality over thousands of kilometers. Landing stations at coastal locations connect submarine cables to terrestrial fiber networks, enabling traffic to flow into cities and across countries. Within metropolitan regions, providers use fiber rings that loop around major population centers. The ring design provides redundancy. If a fiber cut occurs on one segment, traffic can flow in the opposite direction. Regional networks connect cities with long-haul fiber routes, often spanning mountain ranges, deserts, forests, and rural areas. In remote or challenging environments, microwave links supplement fiber, using high-frequency radio waves to bridge longer distances where cabling is difficult. Satellite systems add another layer to global connectivity. Geostationary satellites historically offered communication to remote locations, but experienced high latency because of their altitude. Modern low Earth orbit satellite constellations reduce latency significantly by orbiting closer to Earth. Although satellite networks cannot match fiber in raw capacity, they expand access to underserved regions and provide resilience during terrestrial outages. Data centers are integral to service provider operations. They house servers, networking equipment, storage systems, and cloud infrastructure. Providers use data centers to host customer applications, support cloud services, and deliver content efficiently. Content delivery networks replicate media, software updates, and frequently accessed resources across many data centers. This reduces latency by placing content closer to users and balancing load across regions. End-user connectivity varies widely. Fiber to the home offers high-speed, low-latency connections using optical fiber. Cable broadband uses existing coaxial infrastructure combined with advanced modulation technologies to deliver high throughput. DSL transmits digital signals over telephone lines, offering moderate speeds. Fixed wireless uses point-to-point radio links. Cellular networks provide mobile broadband, with 4G and 5G offering substantial speed and low latency. Satellite provides global coverage where terrestrial infrastructure is limited. Each technology carries different trade-offs, shaped by geography, cost, and deployment constraints. Service providers must manage traffic efficiently to maintain performance. Traffic engineering involves optimizing routes, balancing loads, and avoiding congestion. Protocols like MPLS support predictable routing by attaching labels to packets, allowing routers to forward traffic without deep inspection. Providers use capacity planning to forecast demand and upgrade infrastructure before bottlenecks occur. Monitoring systems track latency, packet loss, utilization, and failures. Automated systems adjust routing based on real-time conditions. Redundancy is essential. Providers maintain multiple upstream connections, diverse fiber paths, backup power systems, and redundant hardware. The goal is continuous operation despite equipment failures, natural disasters, or unexpected demand spikes. Fiber cuts, storms, earthquakes, and equipment outages occur regularly, but redundancy minimizes disruption. Maintenance teams repair physical infrastructure, replace damaged components, and manage environmental controls within data centers. Security is a major responsibility at the provider level. Providers defend against large-scale denial-of-service attacks, capable of flooding networks with massive volumes of traffic. They operate filtering systems that identify malicious patterns, divert harmful traffic, and protect customers. Providers also monitor for route hijacking attempts, where malicious actors announce unauthorized IP prefixes to misdirect traffic. Cooperation between providers, governments, and security organizations helps maintain global routing stability. Providers participate in information sharing groups, coordinate responses to major threats, and enforce best practices for routing security. Peering relationships shape how data flows across the Internet. Peering allows networks to exchange traffic directly without paying third-party transit fees. Some peering agreements are private, connecting networks directly through dedicated infrastructure. Others occur at Internet exchange points, where multiple networks interconnect within shared facilities. Peering improves performance, reduces costs, and shortens the distance that traffic must travel. End users rarely see the complexity behind provider operations. When someone streams a video, loads a web page, or sends a message, their device communicates with local equipment, regional networks, national backbones, and international infrastructure. Packets may cross oceans, pass through dozens of routers, and interact with systems in multiple countries. Yet the experience feels immediate and seamless. This illusion of simplicity is supported by careful engineering, coordination, and planning performed by service providers. The global Internet remains one of the most complex systems ever constructed. It supports communication, commerce, research, entertainment, and essential services across every time zone. Service providers maintain the infrastructure, routing systems, and operational frameworks that keep the Internet running. As demands increase and new technologies emerge, providers continue to adapt, expanding capacity and enhancing reliability. The next chapter explores how applications and services leverage this infrastructure to deliver the digital experiences used every day. Chapter 10: Applications, Protocols, and Digital Services. Modern computing depends on a rich ecosystem of applications and services that run across global networks. These applications allow people to communicate, work, learn, transact, and collaborate regardless of location. Behind every email, video stream, file transfer, or browsing session lies a set of protocols that define how information is requested, delivered, interpreted, and secured. Understanding these protocols reveals how the Internet supports daily digital experiences with consistency and reliability. At the heart of many modern applications is the client-server model. In this design, client devices initiate requests, while servers provide resources, data, or functionality. A web browser requests a page from a web server. An email client retrieves messages from a mail server. A video app asks a streaming service to deliver multimedia content. This division of roles allows servers to run continuously and handle multiple clients simultaneously, while clients remain lightweight and responsive. The model supports scalability, central management, and predictable behavior across networks. The World Wide Web represents one of the most transformative applications in networking history. Its foundation rests on three key technologies: URLs, HTTP, and HTML. URLs provide a uniform way to identify resources. HTTP governs how browsers request those resources and how servers deliver them. HTML describes the content itself. Early versions of HTTP relied on simple request-response exchanges, with connections closing after each transfer. Modern versions, particularly HTTP2 and HTTP3, improve efficiency by supporting multiplexing, header compression, and encryption by default. These enhancements reduce latency and improve the performance of complex websites. Email remains another core application. It operates through several protocols that divide responsibilities. SMTP handles message delivery between servers. POP3 and IMAP allow clients to retrieve messages. POP3 downloads messages for local storage, while IMAP synchronizes messages across devices and maintains them on servers. Email also relies on DNS records such as MX entries, which direct where mail should be delivered. Security extensions like SPF, DKIM, and DMARC help verify sender identity and reduce spoofing. Without these mechanisms, modern email infrastructure would struggle to combat fraud and abuse. File transfer protocols support movement of data between systems. FTP was one of the earliest methods, but it transmits credentials and data in clear text. Secure alternatives, such as SFTP and FTPS, add encryption to protect confidentiality. These protocols enable organizations to exchange large data sets, back up systems, and distribute software. Even as cloud-based methods grow in popularity, file transfer protocols remain essential for automation, system integration, and legacy environments. Real-time communication depends on protocols designed for low latency. Voice over IP converts audio into digital packets that travel across networks using RTP. To maintain quality, systems prioritize timely delivery over perfect reliability. Applications compensate for network jitter, packet loss, and variable latency through buffering and error concealment. Video conferencing adds complexity by transmitting both audio and video streams. Codecs compress data efficiently to reduce bandwidth use while maintaining clarity. Modern platforms rely on adaptive bitrate streaming, selecting appropriate quality levels based on current network conditions. Streaming media services use similar techniques to deliver video and audio to millions of users. Instead of transporting large files directly, servers divide content into segments and deliver only what clients request. Protocols such as HLS and MPEG- allow clients to switch between different encodings as bandwidth fluctuates. This ensures continuous playback even in networks experiencing congestion. Content delivery networks place servers near users, shortening the path data travels and reducing latency. These distributed systems support high demand, ensuring that popular shows, live events, and music streams reach audiences consistently. Cloud applications further expand the role of network-based services. Cloud infrastructure allows organizations to host applications, store data, and run workloads remotely. Users access these resources through APIs or web interfaces. Underlying protocols handle authentication, resource requests, and data transfer. Software-as-a-service platforms rely on stable, encrypted communication to deliver everything from productivity tools to business analytics. The shift to cloud computing increases dependence on reliable networks while reducing the need for local infrastructure. DNS acts as the Internet's phone book. When users type a domain name, DNS resolves it to the corresponding IP address. Recursive resolvers query authoritative servers, caching results for efficiency. Extensions improve security and privacy. DNSSEC signs records cryptographically, preventing manipulation. Encrypted DNS protocols, such as DOH and DOT, protect queries from eavesdropping. DNS plays a silent but essential role. Without it, navigation across the Internet would be impossible. Authentication protocols also support modern applications. Kerberos enables secure, ticket-based authentication in enterprise networks. OAuth allows applications to access resources on behalf of users without sharing passwords. Single sign-on systems integrate multiple services, providing seamless access across platforms. These technologies ensure security and usability while minimizing the friction of repeated logins. Database-driven applications depend on structured communication protocols and query languages. Web applications often interact with back-end databases using SQL queries delivered over secure connections. API-based designs use JSON or XML to exchange structured data. Many modern services implement REST or GraphQL to manage interactions. These approaches simplify development and provide flexible frameworks for building distributed applications. Security remains essential across all application protocols. TLS encryption protects data in transit. Certificates verify server identity. Session tokens maintain continuity while preventing unauthorized access. Application firewalls analyze traffic patterns and block malicious requests. These tools protect both service providers and users from exploitation. Modern protocols increasingly adopt encryption by default, reducing opportunities for interception. Applications also rely on caching to reduce latency and improve performance. Browsers cache web resources. DNS resolvers cache lookups. Content delivery networks cache media and static files. This reduces load on upstream servers and speeds up user experience. At the protocol level, caching headers instruct clients on how long data should remain stored locally, balancing freshness and efficiency. Together, these application layer technologies create the digital experiences used every day. They enable communication, collaboration, entertainment, research, commerce, and automation. Each protocol plays a specific role, coordinating with others to form a consistent and reliable system. As applications evolve, their underlying protocols adapt, incorporating improvements in security, efficiency, and scalability. These developments allow the Internet to continue supporting an increasingly connected world. Chapter 11. Network Monitoring, Management, and Performance. As networks grow in scale and importance, effective monitoring and management become essential. Networks support communication, applications, data services, and business operations. Their performance directly affects the reliability of every digital interaction. Monitoring systems, management frameworks, and performance tools allow administrators to maintain visibility, detect issues early, and optimize resources. Without these capabilities, even a well-designed network can become unstable, inefficient, or vulnerable to disruption. Network monitoring begins with observing the health and behavior of devices and communication paths. Basic monitoring includes collecting information about interface status, bandwidth utilization, error counts, and device availability. More advanced monitoring examines latency, packet loss, jitter, routing changes, CPU load, memory consumption, and temperature conditions. These measurements provide insight into how the network behaves under everyday load and during unusual events. Continuous visibility allows administrators to identify emerging problems before they escalate into outages. One of the foundational tools for monitoring is the Simple Network Management Protocol. SNMP functions through agents on network devices, reporting information to management systems. These agents maintain data organized into management information bases. Monitoring platforms poll devices for metrics, receive traps when significant events occur, and display information through dashboards and alerts. SNMP provides a standardized way to gather information from routers, switches, firewalls, servers, and many other types of equipment. Its flexibility allows organizations to track large networks efficiently. Flow analysis offers deeper insight into traffic patterns. Technologies like NetFlow, IPFX, and SFlow collect metadata about communication flows, source and destination addresses, protocols used, ports involved, and bytes transferred. Flow data reveals which applications consume bandwidth, which hosts communicate frequently, and which segments of the network experience heavy load. This information helps diagnose congestion, detect anomalies, and plan capacity upgrades. Flow monitoring also plays a role in security, highlighting unexpected communication between devices or unusual spikes in traffic. Performance measurement tools analyze the quality of network paths. Latency tests measure the time required for packets to traverse a route. Packet loss tests show where packets are dropped. Jitter measurements evaluate variability in packet arrival times. These metrics hold particular importance for voice, video, and real-time applications. Even small amounts of jitter or loss can degrade audio clarity or disrupt video streams. Performance tools help administrators align network behavior with the requirements of the applications that depend on it. Network management extends beyond monitoring to include configuration control, automation, documentation, and change tracking. Configuration management ensures that network devices follow consistent settings and comply with organizational policies. Automated tools can push configuration updates to multiple devices simultaneously, reducing manual effort and minimizing mistakes. Version control systems store configuration histories, allowing administrators to compare changes over time and quickly revert if necessary. These practices improve reliability and provide a structured approach to network evolution. Automation continues to reshape network management. Instead of manually adjusting settings on each device, administrators define desired states through centralized systems. Software-defined networking expands this concept by separating control logic from individual devices. Controllers manage forwarding behavior across the entire network, enabling rapid reconfiguration, dynamic policy enforcement, and programmable infrastructure. Automation reduces human error, accelerates deployment, and allows networks to adapt more quickly to changing demands. Documentation supports management by preserving knowledge about network structure, addressing schemes, device roles, and topology. Accurate diagrams help teams understand how systems interconnect. Inventory records list equipment models, firmware versions, and physical locations. Cable maps track pathways and terminations. This information becomes essential during troubleshooting, maintenance, and upgrades. Without documentation, networks become difficult to manage and prone to configuration drift. Alerting systems notify administrators when conditions exceed thresholds or when critical events occur. Alerts may trigger when interfaces experience high utilization, when devices lose power, or when routing changes unexpectedly. Effective alerting requires well-designed thresholds and careful tuning to reduce noise. Too many alerts can obscure important issues, while too few may delay detection. Administrators refine alerting rules to match network patterns and operational needs. Troubleshooting requires a disciplined approach. Administrators often begin by isolating the scope of the issue, determining whether the problem affects a single device, a segment, or the entire network. Tools like ping, traceroute, and packet capture assist in diagnosis. Ping tests connectivity, traceroute shows path progression, and packet capture reveals detailed protocol interactions. By combining these tools with monitoring data, administrators identify root causes such as misconfigurations, hardware failures, routing loops, or interference. Capacity planning ensures that networks support future growth. Usage trends indicate when bandwidth upgrades, additional access points, or new routing equipment may be required. Storage capacity for logs and monitoring data must also grow as networks expand. Forecasting demand allows organizations to upgrade proactively rather than reactively, reducing the risk of performance degradation. Capacity planning supports long-term stability by aligning infrastructure with anticipated needs. High availability strategies improve resilience, redundant links, backup power systems, failover mechanisms, and cluster pairs reduce downtime. Monitoring platforms verify redundancy by observing failover events, link status, and load distribution. High availability depends on consistent configuration, synchronized firmware updates, and regular testing. Systems designed with redundancy but never tested may fail when needed most. Ongoing observation ensures that redundancy remains functional. Network health also depends on environmental conditions. Temperature, humidity, airflow, and power stability affect device performance. Data centers require cooling systems, uninterrupted power supplies, and environmental monitoring sensors. Alerts may trigger when temperatures rise, when power conditions fluctuate, or when humidity levels exceed recommended thresholds. Environmental monitoring protects equipment longevity and operational reliability. Security monitoring integrates with operational monitoring. Firewalls, intrusion detection systems, and endpoint protection tools generate logs that reveal attempted attacks, unauthorized access attempts, and suspicious patterns. Combining operational and security monitoring provides a unified view of network behavior. When anomalies occur, administrators can determine whether they stem from failure, misconfiguration, or malicious activity. This integrated approach strengthens both performance and protection. Effective network monitoring and management create a stable foundation for all communication systems. They allow organizations to detect issues early, maintain reliability, plan growth, adapt to changing conditions, and protect against threats. As networks evolve to support new technologies and increased complexity, these capabilities become increasingly important. The next chapter examines how cloud integration, distributed computing, and virtualization continue to reshape network operations and strategy. Chapter 12: Cloud Integration, Distributed Systems, and Virtual Networking. Cloud computing has become one of the most influential developments in modern networking. Instead of relying solely on local physical infrastructure, organizations now combine on-premise resources with cloud platforms to create flexible, scalable, distributed environments. Cloud integration changes how applications operate, how networks are designed, and how services communicate. Understanding the relationship between networks and cloud systems is essential for navigating today's computing landscape. Cloud computing begins with the idea of delivering computing resources as services over a network. Infrastructure, platforms, and applications are accessible through standardized interfaces and scalable architectures. The three most common service models include infrastructure as a service, platform as a service, and software as a service. Infrastructure provides virtual machines, storage, and networking. Platforms offer environments for application development. Software services deliver complete applications through browsers or lightweight clients. Each model relies heavily on stable network connectivity, secure access control, and efficient data flow. Distributed systems arise naturally from cloud architectures. Instead of running applications on a single server, workloads are divided into components that communicate across networks. These components may run in different data centers, different regions, or even different cloud providers. Distributed systems offer advantages such as redundancy, load balancing, and parallel processing. However, they also require careful design to manage synchronization, consistency, and fault tolerance. Network performance plays a critical role. High latency can slow coordination, while packet loss can disrupt communication between components. Virtual networking supports these distributed designs. In cloud environments, virtual networks function like traditional networks but exist entirely in software. Administrators define subnets, routing rules, security groups, and gateways. Virtual routers forward traffic, virtual firewalls enforce policies, and virtual load balancers distribute workloads across servers. This abstraction allows rapid deployment, flexible reconfiguration, and consistent behavior regardless of underlying hardware. It also enables isolation, ensuring that applications and tenants remain separated even when sharing the same physical infrastructure. Hybrid cloud designs extend on-premise networks into cloud environments. Virtual private networks create encrypted tunnels between local infrastructure and cloud subnets. Dedicated connections offer higher performance and lower latency for organizations with demanding workloads. Routing integrates private and cloud networks, allowing seamless communication. Proper design prevents routing loops, establishes priority paths, and ensures predictable behavior. Hybrid approaches help organizations maintain control of sensitive data while leveraging the scalability of cloud platforms. Containerization adds another layer to distributed computing. Containers package applications and dependencies into lightweight units that run consistently across environments. Container orchestration systems, such as Kubernetes, coordinate deployments, scaling, and networking. These systems rely on virtual overlays that assign each container its own network identity. Service discovery systems maintain internal DNS mappings, allowing components to find one another. Network policies regulate which containers may communicate. These mechanisms create dynamic, modular application stacks that adjust quickly to demand. Service meshes further enhance communication within containerized environments. A service mesh provides traffic management, encryption, retries, circuit breaking, and observability at the application layer. Instead of individual applications implementing these features, service meshes handle them through sidecar proxies or embedded agents. This separation simplifies development and ensures consistent behavior across services. Service meshes rely on strong network reliability as they introduce additional communication steps and require careful tuning to maintain performance. Storage also plays a major role in cloud integration. Distributed storage systems divide data across multiple nodes, ensuring redundancy and availability. Block storage, object storage, and file storage each support different use cases. Object storage systems are particularly common in cloud environments due to their scalability and durability. Access to storage requires stable networking, consistent throughput, and strict access control. Replication across regions increases resilience, but depends on reliable inter-region communication links. Security in cloud networking integrates identity, encryption, segmentation, and continuous monitoring. Cloud environments use role-based access control to manage permissions. Identity and access management systems define which users and services can modify resources. Security groups act as virtual firewalls, controlling traffic to and from instances. Network access control lists add additional layers of filtering. Encryption protects data during transmission and storage. Logging systems record configuration changes, authentication events, and communication patterns, providing visibility into cloud activity. Performance optimization remains critical in distributed systems. Latency between regions affects application behavior. Bandwidth dictates how quickly large data sets can move across environments. Load balancers distribute traffic based on health checks, resource utilization, and geographic considerations. Edge computing extends processing closer to users, reducing latency and improving responsiveness. Content delivery networks replicate static content to edge locations, reducing load on central servers and minimizing travel distance for data. Fault tolerance and resilience are defining features of distributed architectures. Applications often run across multiple availability zones or regions. If one component fails, others continue functioning. Health checks detect failures and trigger replacements. Auto-scaling systems allocate additional resources when demand increases. Redundant links ensure connectivity between regions. These features prevent single points of failure and support continuous operation. Observability tools assist with managing the complexity of distributed systems. Metrics track performance. Logs capture detailed events. Traces map interactions between services. Observability platforms combine these signals to provide a unified view of application behavior. They help administrators identify bottlenecks, detect anomalies, and tune performance. Because distributed systems have many components, observability becomes indispensable for reliable operation. Cloud integration also influences cost management. Usage-based billing requires careful monitoring of compute hours, storage, data transfer, and reserved resources. Network traffic between regions or providers may incur significant charges. Administrators optimize architectures to reduce unnecessary transfers, minimize idle resources, and select appropriate service tiers. Cost efficiency becomes a design factor alongside performance and reliability. Together, cloud integration, distributed systems, and virtual networking reshape how modern networks operate. They create environments that scale, adapt, recover, and evolve rapidly. Applications no longer depend solely on single data centers or traditional architectures. Instead, they run across complex ecosystems designed for global use. Understanding these systems prepares us for the final chapters, which explore emerging trends and the future direction of networking technologies. Chapter 13: Emerging Technologies and the Future of Networking. Networking continues to evolve as new technologies reshape how devices communicate, how applications operate, and how infrastructure adapts to global demand. The future of networking is not defined by a single innovation, but by a combination of trends that change how data flows across systems. These developments influence performance, security, reliability, scalability, and the overall design of digital environments. Understanding emerging technologies helps prepare for a future defined by rapid growth and constant transformation. One major area of change is the expansion of the Internet of Things. Billions of sensors, appliances, industrial machines, vehicles, and wearable devices now connect to networks every day. IoT devices generate continuous streams of data, often with small packet sizes but high message frequency. Traditional networks were not designed for this density of endpoints. New protocols and architectures support efficient IoT communication. Low-power wide-area networks, such as LoRaWAN and Sigfox, allow long-range, energy-efficient transmission. Short-range protocols, including Bluetooth Low Energy and Zigbee, support home automation and industrial monitoring. IoT requires scalable addressing, efficient data management, strong security, and careful segmentation to prevent vulnerabilities from spreading. Edge computing represents another significant development. Instead of sending all data to centralized cloud platforms, edge systems process information closer to the devices that generate it. This reduces latency, conserves bandwidth, and improves responsiveness. Applications such as autonomous vehicles, industrial automation, and real-time analytics depend on split-second decisions. Edge servers, micro data centers, and gateway devices provide localized computing power. Networks support this design by offering high-speed links between edge nodes and central systems, enabling hybrid processing models that combine local and cloud resources. 5G networks further expand mobility and high-performance communication. Fifth-generation cellular technology increases throughput, decreases latency, and supports dense device environments. 5G networks use a combination of low-band, mid-band, and millimeter wave frequencies. Low-band frequencies provide wide coverage. Mid-band frequencies offer balanced performance. Millimeter wave frequencies provide extremely high throughput at short range. Network slicing allows operators to allocate dedicated virtual networks for specific applications, providing tailored performance characteristics. 5G supports IoT, augmented reality, remote robotics, and real-time monitoring systems, creating new possibilities for mobility and communication. Artificial intelligence and machine learning also play growing roles in network management. Networks generate massive amounts of telemetry, logs, and performance data. AI-driven analytics identify trends, detect anomalies, predict failures, and recommend optimizations. Automated incident response systems use machine learning models to identify malicious traffic, isolate compromised devices, or adjust policies. AI enhances efficiency by optimizing routing decisions, adjusting bandwidth allocation, and tuning wireless settings dynamically. As networks grow more complex, intelligent automation becomes essential for stability and performance. Quantum networking introduces a new frontier. Although still in early stages, quantum communication uses quantum states to transmit information. Quantum key distribution provides theoretically unbreakable encryption by detecting any attempt to intercept communication. Quantum repeaters, entangled photon networks, and quantum memories are subjects of ongoing research. If realized at scale, quantum networking could revolutionize secure communication and create new architectures for distributed computing. Another emerging trend is the growth of optical networking. Modern optical technologies improve speed, reduce power consumption, and support vast data throughput. Dense wavelength division multiplexing allows multiple signals to travel over a single fiber strand by using different wavelengths of light. Coherent optical communication improves signal integrity over long distances. These innovations support the bandwidth demands of cloud providers, streaming platforms, scientific research, and international connectivity. Optical networks are becoming the backbone for future expansion. Software-defined wide-area networking transforms how organizations connect distributed sites. Traditional wide-area networks relied on fixed circuits and static routing. SD-WAN abstracts control into software, allowing centralized policy enforcement, dynamic path selection, and application-aware routing. SD-WAN reduces costs by combining private circuits with broadband or wireless links while maintaining security through encryption and segmentation. This technology improves flexibility for organizations with remote offices, mobile workers, and cloud-based workloads. Zero-trust networking also continues to grow. As workforces become more distributed and applications move to the cloud, traditional perimeter-based security becomes insufficient. Zero Trust treats every user, device, and application as potentially untrusted. Continuous identity verification, microsegmentation, encryption, and telemetry support a model where trust is earned dynamically. Networks incorporate identity-aware proxies, secure access service edge architectures, and context-based access policies. This approach reduces risk and aligns security with modern workflows. Blockchain technology influences certain network designs as well. Decentralized systems store data across distributed ledgers, enabling transparent, tamper-resistant records. Networking applications include secure record sharing, decentralized naming systems, and trust frameworks. While blockchain is not suitable for all use cases, it provides models for building resilient, auditable communication frameworks. Sustainability increasingly shapes the future of networking. Large data centers and global infrastructure consume significant power. Initiatives focus on improving energy efficiency, reducing heat output, and optimizing cooling systems. Renewable energy sources power more network facilities. Equipment manufacturers design switches, routers, and servers with lower power consumption. Sustainable practices help reduce environmental impact while supporting continued growth in digital infrastructure. Interoperability remains a key requirement. As new technologies emerge, networks must integrate with legacy systems, cloud platforms, edge nodes, and diverse devices. Standards bodies develop protocols that ensure compatibility and predictable behavior. Open source projects accelerate innovation and create shared frameworks that organizations adopt widely. The future of networking depends on collaboration across industries, research institutions, service providers, and hardware manufacturers. These emerging technologies collectively influence how networks evolve. They enable faster communication, greater automation, stronger security, and broader connectivity. The next chapter explores how these trends integrate into operational strategies, preparing networks for long-term growth, resilience, and adaptability. Chapter 14: Scalability, Resilience, and High Availability Network Design. As networks expand and support increasingly diverse workloads, scalability and resilience become essential design considerations. Networks must accommodate growth without disruption, maintain performance during peak demand, and continue operating when individual components fail. High availability strategies, redundancy models, and scalable architectures allow networks to meet these expectations. Understanding these elements prepares organizations to build systems that function reliably under changing conditions and growing requirements. Scalability begins with the ability to handle more devices, more traffic, and more applications without sacrificing performance. Horizontal scalability increases capacity by adding additional devices, such as switches, routers, access points, or servers. Vertical scalability increases the performance of existing equipment through upgrades or configuration enhancements. Effective network design often blends both approaches, ensuring that critical systems can expand gradually rather than requiring complete redesign. One of the simplest strategies for scalability is modular design. Modular switches allow administrators to add line cards, increase interface density, or introduce higher speed ports as needs evolve. Modular firewalls and load balancers follow similar patterns. This approach reduces the need for wholesale equipment replacement and provides predictable upgrade paths. Modular systems also simplify maintenance since components can be replaced individually without affecting the entire device. Scalable networks rely on predictable topologies. Hierarchical architectures provide clear boundaries between access, distribution, and core layers. As traffic grows, organizations can add additional access switches or increase the bandwidth of uplinks. Distribution and core layers can be upgraded to higher capacity equipment. Spine and leaf architectures, common in data centers, offer near-linear scalability. Every leaf switch connects to every spine switch, creating predictable paths with minimal latency. As demand rises, administrators add more spine switches or expand leaf capacity. Virtualization enhances scalability by abstracting network functions. Virtual routers, virtual switches, and virtual firewalls can scale up or down quickly. Administrators adjust resource allocation or deploy additional virtual instances to support new workloads. Cloud environments extend this concept further. Instances, containers, and virtual networks scale based on demand, often automatically. This elasticity helps organizations match capacity to usage patterns, reducing waste and improving responsiveness. Resilience focuses on continuity during failures. A resilient network continues operating even if individual components malfunction. Redundant links provide immediate alternate paths. If one link fails, Traffic flows through the remaining connections. Link aggregation bundles multiple physical links into a single logical connection, increasing both bandwidth and resilience. Redundant devices provide additional protection. Core switches, distribution switches, and routers often operate in pairs. If one device goes offline, its partner continues supporting traffic. Routing protocols support resilience by adapting to changes. OSPF and ISIS use link state databases to calculate shortest paths. If a link fails, they detect the change quickly and update routes. BGP supports redundant internet connections by selecting alternate paths when upstream providers experience issues. This dynamic behavior ensures that networks remain reachable even during physical or logical disruptions. High availability protocols maintain stability at the gateway level. Technologies like VRRP, HSRP, and GLBP allow multiple routers to share a virtual default gateway. If the active router fails, another takes over immediately, preserving communication for connected devices. These protocols minimize downtime and prevent route recalculation delays. Failover mechanisms provide redundancy for firewalls, load balancers, and security appliances. Active-passive pairs maintain standby devices ready to assume control if needed. Active-active configurations operate multiple devices simultaneously, increasing performance while providing backup capacity. Synchronization ensures that both devices share session information, configuration states, and security contexts. Load balancing enhances both scalability and resilience. Load balancers distribute traffic across multiple servers or service endpoints. When one server becomes overloaded or fails, the load balancer redirects traffic to healthier nodes. Application-level load balancing considers factors such as response time, resource usage, and geographic proximity. Global load balancers extend this concept across regions, improving performance and reliability for users worldwide. Data plane and control plane separation also influence resilience. In traditional networks, each device performs its own forwarding decisions and control logic. Software-defined networking centralizes control in a controller, which distributes forwarding instructions to switches. This model simplifies network management and accelerates failover. If one switch fails, the controller redirects traffic through alternate paths, maintaining service continuity. Environmental resilience remains equally important. Networks rely on supporting systems such as cooling, power distribution, and physical security. Uninterruptible power supplies protect equipment during outages. Generators maintain power during extended failures. Precision cooling systems manage temperature within data centers. Physical access controls prevent unauthorized tampering. Environmental monitoring sensors alert administrators to humidity changes, power anomalies, or airflow issues. These safeguards prevent failures that stem from non-network factors. Disaster recovery extends resilience across geographic regions. Organizations replicate critical data and services to secondary sites. If a major event disrupts the primary location, backup systems activate. Networks support disaster recovery through high-capacity intersite links, redundant routing paths, and synchronized storage systems. Recovery plans outline how traffic transitions between sites, how applications start up, and how data consistency is maintained. Testing ensures that resilience strategies function correctly. Failover events must be validated through controlled drills. Routing changes, device replacements, and link failures must be observed to confirm that transitions occur smoothly. Documented procedures help teams respond confidently during real incidents. Regular testing reveals configuration issues, outdated assumptions, or unexpected dependencies. Scalability and resilience often intersect. A network that scales easily may also provide additional pathways for redundancy. Conversely, a resilient network with multiple pathways must ensure that added complexity does not hinder scalability. Balancing these factors requires careful planning, clear documentation, and continuous evaluation. As networks evolve, administrators refine architecture to match current demands while preparing for future growth. Together, scalability, resilience, and high availability design form the backbone of reliable network infrastructure. They ensure that networks remain responsive, adaptable, and durable even under pressure. The next and final chapter integrates these concepts into a broader perspective, examining how modern networks achieve long-term stability, sustainability, and readiness for ongoing technological change. Chapter 15: Long-Term Stability, Sustainability, and the Evolution of Network Infrastructure. As networks mature and technologies evolve, long-term stability becomes a central priority. Modern infrastructure supports global communication, essential services, scientific research, and economic activity. Ensuring that these systems remain dependable requires thoughtful planning, sustainable design, and a willingness to adapt. Long-term stability is not achieved through a single technique, but through an interconnected set of practices that guide how networks are built, managed, and extended over time. Sustainability plays a larger role in network design each year. Data centers, service provider networks, and enterprise infrastructures consume significant amounts of energy. Equipment manufacturers respond by designing switches, routers, and servers that use power efficiently. Newer chipsets reduce heat output, support dynamic power scaling, and operate at higher performance per watt. Network operators adopt strategies that reduce energy use without compromising availability. These include consolidating workloads, optimizing cooling, and using renewable energy sources to power facilities. Sustainability not only reduces environmental impact, but lowers operational costs and increases the long-term viability of large-scale infrastructure. Stability begins with predictable, well-documented architecture. Modern networks function best when designed with clear boundaries, consistent addressing, organized segmentation, and standardized hardware. Regular reviews ensure that design choices remain aligned with organizational goals. As requirements evolve, networks expand methodically rather than improvisationally. Documentation supports this process by providing a map of devices, dependencies, routing policies, and physical pathways. When teams rely on shared knowledge rather than individual memory, systems become more resilient to turnover, growth, and unexpected problems. Lifecycle management contributes to long-term reliability. Every network device has a finite lifespan. Hardware ages, firmware becomes outdated, and components eventually fail. Lifecycle planning identifies when to retire, replace, or upgrade devices. This prevents emergency outages caused by aging hardware and ensures that security patches remain available. Hardware refresh cycles also improve performance, reduce power consumption, and incorporate updated standards. Lifecycle management aligns infrastructure with the pace of technological advancement. Standardization improves interoperability and reduces complexity. Organizations adopt standardized models for cabling, rack layouts, addressing schemes, routing protocols, and security policies. Standardization allows new devices to integrate smoothly, simplifies troubleshooting, and creates predictable behavior across the network. It also supports automation by ensuring that configuration templates can apply to many devices. As networks become more automated, standardization becomes even more important for consistency and reliability. Governance frameworks guide long-term stability by establishing rules for how changes occur. Change management processes ensure that modifications to routing policies, firewall rules, or configuration templates undergo review before deployment. Impact assessments predict how changes might affect services. Maintenance windows reduce the risk of disrupting critical operations. These processes balance innovation and caution, enabling networks to improve while preserving stability. Monitoring and analytics support long-term planning. Historical data reveals patterns of growth, emerging bottlenecks, and recurring issues. Performance metrics indicate when additional capacity is required. Security telemetry shows which threats appear most frequently. By studying these signals, organizations make informed decisions about upgrades, segmentation, expansion, and risk mitigation. Analytics transform raw data into strategic insight, helping networks evolve deliberately rather than reactively. Training and knowledge development contribute to sustainable operations. Networks rely on skilled professionals to manage routing, switching, security, virtualization, automation, and cloud integration. Continuous learning ensures that teams understand new technologies, standards, and methodologies. Training reduces configuration errors, improves troubleshooting efficiency, and supports innovation. Mentorship programs preserve institutional knowledge, helping teams maintain stability even as personnel change. Collaboration across teams also influences long-term reliability. Network engineers, security analysts, system administrators, developers, and cloud architects work together to design integrated solutions. Modern networks intersect with application development, cloud platforms, storage systems, and virtualization. Coordinated planning ensures that changes in one area do not unintentionally disrupt another. Cross-disciplinary communication strengthens stability and accelerates problem resolution. Risk management forms a core part of long-term planning. Networks face risks from hardware failures, cyber attacks, natural disasters, supply chain disruptions, and human error. Organizations assess these risks through structured methodologies, identifying vulnerable components and critical dependencies. Mitigation strategies may include redundant infrastructure, strong authentication, incident response plans, and geographically distributed services. Regular testing validates preparedness. Risk management ensures that networks remain functional even when confronted with unexpected challenges. The evolution of networking continues through emerging technologies. Edge computing reduces latency by moving resources closer to users. Optical innovations support higher bandwidth across continents. Quantum communication promises secure key distribution. AI-driven automation enhances monitoring and performance optimization. Virtualization expands abstraction and flexibility. These technologies shift how networks function, requiring continuous adaptation. Long-term stability does not mean resisting change. It means integrating new capabilities intentionally while preserving reliability. Sustainability intersects with innovation. Energy-efficient hardware supports advanced features without increasing power consumption. Intelligent cooling systems reduce waste. Renewable energy sources support large facilities. Green networking initiatives encourage organizations to measure and optimize environmental impact. These efforts reflect industry-wide recognition that digital infrastructure must evolve responsibly. Operational resilience depends on continuous improvement. Lessons from outages, incidents, and near misses become guidance for future design. Documentation updates reflect new insights. Monitoring thresholds adjust based on observed behavior. Configuration templates evolve to incorporate best practices. Networks that learn from experience grow stronger. Continuous improvement transforms individual improvements into long-term stability. User expectations also shape network evolution. As remote work, mobile devices, cloud platforms, and digital services become essential, the need for reliable connectivity increases. Networks must support high-quality video conferencing, large-scale collaboration, streaming media, and real-time applications. Latency-sensitive workloads require consistent performance. Security-conscious environments demand strong protection. Meeting these expectations requires sustained planning, investment, and adaptability. In the end, long-term stability arises from a combination of good design, responsible management, proactive planning, and continuous adaptation. Sustainable practices support operational efficiency. Governance frameworks maintain consistency. Monitoring and analytics guide decisions. Training builds expertise. Innovation adds new capabilities, while respect for foundational principles preserves reliability. Networks evolve, but the need for stability remains constant. This final chapter concludes the exploration of computer networks as a layered, interconnected, and continuously advancing field. From early packet switching to global cloud platforms, networks have become the foundation of modern digital life. Their future depends on careful design, resilient architecture, sustainable practices, and the willingness to evolve with emerging technologies.